Hey everyone, welcome to our Deep Learning Algorithms course, where we're going to be focusing on neural networks and how they are used in various scenarios in order to drive various AI applications. Alright, so we're going to be looking at various structures such as neural networks, and then we're going to look at more advanced structures as well, such as convolutional networks and transformers. Alright, they're not that much different, but they do have various differences that are important to know. Alright, so we're going to learn how to optimize these algorithms, and we're going to learn how to just implement them in either JavaScript or R, and then we'll just get into the theory about how a neural network actually works. Alright, so the basics of a neural network is a model inspired by the way a brain works. Alright, so they classify it as containing a bunch of neurons which are in your brain, and they all fire to each other more or less. And once we have millions of neurons, each firing different signals, they eventually work together in order to come up with a rational result. Alright, and that's more or less how the neural networks work inside of a computer. So we try to simulate the brain, and we use this more or less simulation to recognize patterns as well as classify data and make predictions based on previous input data. Alright, so as you can see here on the right, I got a nice little example of what a neural network can look like. So for example, we have for our first property of a neural network are neurons and layers. Alright, so as you can see here, I just labeled them N1, N2, N3. These guys are called neurons, and that's more or less your inputs as well as the values that are going to be calculated throughout. So in our first column here, this is called your input layer. So that's where you're going to put in values, and then once we put in those values, they're going to be calculated forwards to our hidden layers, which of course are the middle layers. So I'll just put a little thing here, input, and then the middle two are always your hidden. There could be 4, 5, 6, or even one hidden layer, but something that's in between the input and the output is a hidden layer. All right, and then of course your last column is your output. All right, so that's more or less how it works. So this would be layer 0, and then you'd have layer 1, layer 2, layer 3. Or I guess you could just look at it in the form of hidden layers too. So it'd just be a 2-layer neural network, either way. So that's what a neuron and a layer is with respect to a neural network. And then the next most important thing we need to learn about is weights and biases. All right, so a bias here is just something that you tack on just one single time into each layer. All right, so for our input, you can see there's a bias 1 here, a bias 2 in the first hidden layer, and then a bias 3 in the second hidden layer. All right, and what these guys do is just kind of, well, as it's in the name, just provides a bias for your calculations. And then with each of these neurons and each bias, you can see that there are all these lines attached to other neurons. And what these are called are weights. All right, and these are generally initialized to be a value between 0 and 1, but there's other ways to randomize it as well. It could be -1 and 1. And either way, every single line here is going to have a weight. All right, so I'm just going to call it, weight 1, weight 2, and etc. And likewise, neuron 1 will also have a weight 1, weight 2, weight 3, and then of course, neuron 2 itself will have a weight 1, weight 2, weight 3. And of course, this usually gets stored as a matrix or just like a 2D array where you just keep track of each node's weight with respect to the next node. Anyways, once we have these weights and biases sorted out, we can look into our propagation. So a neural network works by just calculating the next node through basic multiplication. So we got N3 here. So in order to calculate N3, what we'd have to do is we would grab the bias 1 and then grab the weight of that guy there. So times the weight 1 for him, plus, and then we'd go to the next node and find that line. So then N1 times its own, sorry, I got a little typo there, times its own weight. So just make sure that weight 1 is unique to each neuron here. And then you do again plus N2 times weight 1. All right, so that's how you're going to calculate the actual node value inside of the next neuron through forward propagation. And then of course this would just apply to the next node as well. So we have n4 hanging out here. Then it would be equal to, you know, the bias 1 times weight 2, and then plus n1 times its own unique weight 2, plus n2 times its unique weight 2. All right, so it's the same idea. You just got to make sure you differentiate which weight you're using for which node you're propagating to. All right, so just make sure it's stored in a 2D array usually. And if you use a process such as matrix multiplication, it makes it a little bit more efficient to understand and a little more automated as well, which is pretty nice. Either way, this presents us with our next problem with a neural network, though, which is how we need to use something called activation functions. All right, so for example, say all of these values are equal to 1, and then all the weights are initialized to 0.5, which wouldn't usually happen in theory, but that'd give us 0.5 plus 0.5 plus 0.5, all right? And that would give us an answer of 1.5, okay? And in our case, we actually don't want this, okay? And that's because when we multiply through our neural network, we're going to have an output, and most of the time it's not going to be continuous, so you don't want it to be a value that's greater than 1 or 0. And that's because a lot of the times, and for this example, I'll use something called like spam emails. You only have two options, right? 1 being spam and 0 being not spam, okay? In our case here, we have two output nodes. So the top node, we'll say, is the probability of it being spam, and the bottom node will be the probability of these inputs being not spam. So what we're going to do is, say, for example, after propagating it all, we get 0 and then 0.5. Sorry, 1 and 0.5. If we look at these two nodes now, we can see that the top node has a higher value, and since that node corresponds with the probability of being spam, we know that it's going to be a spam email, all right? Or we're going to classify as a spam email. And likewise, if the bottom node was higher or a bigger number, we'd say it's not spam, okay? So for example, if we calculate n3 to be equal to 105, then that's a really big number, and it's going to be almost impossible for that big value to not override every other node, okay? Because it's just such a big number. When we're going to propagate it forwards, all these nodes are going to be calculated to be super big numbers, all right? Because our weights aren't going to be that small initially, especially. So maybe they'll get calculated to something really small, like 20, 30, and 50, all right? And that one big number just completely threw everything out of proportion, because then all these guys are going to be calculated to be big numbers as well. And when everything gets calculated to be a big number as well, then it's kind of hard for it to learn and be like, hey, this is spam or isn't spam, right? They're just such big numbers that it doesn't know what to do, okay? So in order for us to actually interpret it better, what we're going to use is activation functions. And when we use an activation function, it more or less is going to take our number, no matter how big or how small, and then it's going to more or less normalize it to be a value between typically 0 and 1. It could do -1 and 1 as well. It depends on which one you use, all right? So in our case, we'll just say sigmoid, for example. And when we put a large number in, such as 105, it's going to spit out a decimal point, which like is just 0. I'll probably be a little bigger than that, 0.85. And that means instead of having this super large number that's going to get propagated forward, that's going to pretty much make every neuron say this is a spam email, then we're going to put in 0.85 instead. All right, and that's just going to say it has still a high likelihood of being spam, but now we're in our range where if we do want to calculate it forwards with our weights, then we won't have as much of a problem with the rest of the neural network being taken over. All right, and then you're going to apply this to every single node, okay? So just think about activation functions as a way to normalize the data. So our outputs from multiplying these nodes and biases together, it just keeps things from being nonlinear, all right? Because when you get to really big numbers, just know that it's not good, and we need to normalize it in order for the neural network to learn properly and more efficiently. So after we do our little activation function for all these nodes and multiply it all forwards, we're of course going to be left with the value, as I said, like a 1 and a 0.5, we'll say. And all we got to do now is calculate our error each time we do one of these calculations. So for each data or each row of data in the table, all we have to do now is calculate the error after we get our input and output. So for example, we get this output 1 and 0.5, we're going to say this email is spam because the top node is a bigger number. In our case, say we're wrong. So say the training data tells us that that is not spam email. Then that should tell us that this node's value should have been 0 and this node's value should have been 1. Okay, so what we're going to do then is calculate the error. So this guy would be off by an error of 1, so it's the difference, because it should have been 0. So 1 minus 0 equals 1. And then this guy was off by 0.5 because he should have been 1 because he wanted this number to be bigger, not spam, and instead he's a 0.5. So his error is 0.5. So he's got a little bit less of an error, but he's still wrong. So then what we're going to do then is calculate how far off we were. Okay, so in our case, I guess we just calculate that. So we're going to take how far off we were, and then we're going to multiply our weights by that. All right, so we're going to calculate new weights based on how wrong we were, and then we're going to do that all the way backwards. So all the nodes connecting to the top node are going to be changed more heavily than the ones on the bottom, which will be changed slightly less heavy. All right, and then each time we calculate a new row value, we're going to do the exact same thing. So then we're going to do, for the second row, calculate all forwards, calculate the error, back propagate it, and change the weights. And then we're going to do that until we do every row in the table. And that's going to be called one epoch. And once we do one epoch, that means, we went over all the data once, and we could choose to do it again. And in a perfect world, it'd be nice to only do it once, but generally, neural networks have to train for tens, hundreds, or sometimes thousands of epochs in order for their weights to work properly. All right, so just have that in mind, that if your data isn't working as intended, sometimes you just need to train it longer with more epochs. And yeah, that's just going to change the weights based on the error each time. And in theory, your weights should start to hone in on specific values that will provide less and less error on your training data. And then usually you would just train until you have like 90 to 95% accuracy, because if you go too high on the accuracy side, then you can risk overfitting. And overfitting just means that if you have a slight outlier, then it's not going to pick it up, etc. And it might make some mistakes if you have any variance in your data. All right, so that's more or less how the propagation portion works of it, and that is how we change our weight values for our neural network to actually learn. All right, so those are the 4 main aspects of a neural network. So now we can just talk about quickly their use cases and types of neural networks. So the first type of neural network that we're more or less looking at now is a basic neural network, and this is best for table data. So that just means you have a bunch of inputs. So we could just say this type of flower, we could take the petal length, the stem length as an input, and then we know on the other side of the table there's going to be a species of flower, all right? And then the neural network would take those lengths and then calculate them forwards, give us an output, all right? Super basic. And then another type, which is a little more complicated, is a CNN, so the convolutional neural network. And this is best for grid out inputs, such as images. So if you have a nice square that's a 9 by 9 in pixels, so there's 81 squares, you could, have it filled out with a bunch of dots, which would be represented as ones or zeros, and then you could use that grid data in order to, maybe it's going to read what number is inside of it. So it has 23 pixels that fill out to be equal to a 1, then this guy could, take in that grid, and then once he learns which nodes need to be, filled out for it to be equal to a 1, then it could identify it for us. So in this case, we'd have, 81 inputs, right? Because there's 81 pixels that we have to worry about. All right, so that's why I use a convolutional neural network. They're just more efficient at this kind of data. And of course, those can be used for images as well, or videos. All right, and the last one we're going to talk about are transformers. And all you need to know about transformers is that they're good for sequential inputs, such as text. So like a basic neural network, we have the flower lengths, but they're not really related to each other. But with something such as text, like the word axe, you need to consider the inputs prior to it in order to actually determine if it has value, right? So an E on its own doesn't really have much value, and an XE doesn't have much value, but if you put AXE, oh, that's a word all of a sudden. So you want to use this kind of neural network if you have to worry about sequential data where, the inputs need to be side by side and calculated together, more or less, or verified together in order to make sense. But yeah, either way, that's more or less how neural network works. We really oversimplified the process and how the calculations work, but that we do have a solid understanding of what's going on behind the scenes. We're going to be using, again, libraries in order to emulate these neural networks or actually create neural networks. So we just have to really know what these properties are. And once we know what these properties are, as well as how to alter them and know why we should alter them, then we can get a lot more use out of the library, such as like TensorFlow, in order to actually utilize these networks. So yeah, that's going to do it for this video, and in the next one, we'll get ourselves some dummy data, and we will try to make ourselves a basic neural network inside of either JavaScript or R. I haven't decided yet, but once we've done that, then we can yeah, give it a try, and then go over when we should use activation functions, where to do that, as well as, yeah, what TensorFlow is doing behind the scenes, more or less. So yeah, I'll see you guys in the next one. Thank you. Hey everyone, welcome back to our Deep Learning Algorithms course, where we're going to be diving into actually creating ourselves a neural network. And I've used this example in another course, but it's just a really good sample, and we can do lots with it. So I'm going to be using the iris data example, where we just have a bunch of characteristics about flowers, such as their sepal and their petal length, and then based on the data we put in, it's going to spit out what species of flower it is. All right, so it's just going to have 2 inputs and 1 output. All right, and of course, if you want to use data that has more inputs, the process is going to be exactly the same. You just got to change or tweak a couple things in terms of the actual training portion. All right, and we'll get into that if you want to use different data as well. You just got to make sure that your data is actually valid, as in there can actually be a pattern. Otherwise, you won't know if your network is working. And yeah, you should be good to go. All right, so to get started with all this, I'm going to include this in the source code, but I don't really want to. It's just a basic HTML to import brain.js. So what we're going to do is, you can just copy it from the source code I'll have in there if you want. But yeah, it's just basic HTML code. And then the only difference is that we're going to be importing script.js, and then we're going to be importing script. And then this is just a CDN link, which is going to bring you to brain.js. So if you want to click on it, it's just a bunch of code, more or less. All right, and that's just the library itself stored inside of a file online. Okay, so just make sure you have it typed out properly, and then once we do that, yeah, we should be good to go. All right, so to get started with our actual data, I'm also going to post this inside of the notepad or inside of our source code, because it is quite tedious how many there are. We just have 30 data points. Honestly, you'd usually have more in this original data set, but I decided to break it down a little bit so it was more readable. All right, and also you'd usually parse this out in an Excel file, but I just figured I would put it into a table for us already, because we're using a browser like this already. So yeah, we don't have any way to actually upload a CSV this way. Anyways, so this is our data. We have, I think maybe it's 20 data points for each flower, and then the characteristics. And then all we're going to have to do now is figure out how we want to actually train a neural network and how we want to tackle this problem. So we have this big data that, of course, you can copy in from the source code. And then the first thing we're going to do actually is normalize our data, all right? And this just means what we're going to do is, for each of these values, what we're going to do is find the very maximum and the very minimum value for both sepal length and petal length across the whole table. All right, so it doesn't matter what type of flower it is, we're going to find the min and the max. And what we're going to do is, when we go to train our network, instead of putting in 7.2 for our input node or 6.0 in for our other input node, what we're going to do is that we're going to make that be equal to a ratio between the maximum and the minimum. So if, say, 7.2 is our longest sepal length, if we were to put this into our neural network, normalized, it'd be equal to 1. All right, likewise, if we put in, go all the way to the top, like the sepal length be equal to 4.8, that's going to be equal to like 0.6 instead of that value, right? Because 0.6, it's like 60% of 7.2. All right, and that's just so our values, again, stay small, because we want our values to be between 0 and 1 typically with a neural network, so stuff doesn't blow up. All right, if you don't normalize your data, then you're going to have some issues with with how to figure it out, or how to actually train your model. All right. Likewise, if you have, say you have another input that is a string, you can use something called hot1 encoding, which I cover in another course, in order to actually normalize that data as well. All right. And we might get into that another time, but for this time being, we're just going to have numbers. So to normalize our data, what we're going to do is actually find our min and our max. So we could just create a little algorithm that could find the min and the max for us, but I just combed through it quickly and found it ourselves to save us some computing time. So I'm going to do sepal length minimum. So we're going to find the minimum and the maximum. And let's get rid of this equal sign. So sepal length minimum is equal to 4.3, and then sepal length maximum is equal to 7.9. All right, and then we're going to get our const petal length min equal to 1.0, and then petal length max is equal to 6.9. All right, so in order to actually use these to normalize, all we have to do is going to do function normalize data. So we're going to pass our table into this afterwards. And all we're going to do is return another table, but it's going to be mapped. So data.map, and then we're just going to call it D for data. Doesn't really matter. And then that should be good to go. I'm sure I messed up a bracket somewhere. Either way, how it's going to work is, in this new table, we're going to have sepal length, and then that's going to be equal to, and then our normalization formula. So we're going to do the actual value, so the actual sepal length minus our minimum, and then we're going to divide that by our max. So then we're going to do sepal length max minus d dot sepal length. All right. And I think it's our sepal length min, actually. Yeah, it's max minus min. So what we're going to do is get our sepal length minus the min over the max minus the min. And that will always return a value between 0 and 1 with respect to our maximum minimum. All right. Then what we're going to do is the exact same thing for our petal length to normalize it. So d dot petal length minus petal length minimum divided by petal length maximum minus petal length minimum. All right, it's kind of a pain. All right, and then of course we still need in our data our species column, but we don't have to mess with that at all because that's our output. So we need the output, but we don't need to actually mess with it at all. And we're going to do species colon d dot species. So we're just going to parse it that way. All right. And then once that's sorted out, I just got to figure out how I messed up some of these values here. Syntax. There should be a comma between them. Oh, that bracket's supposed to be here. That's why. My bad. And once we have that sorted out, put a comma after this guy. And then we just got to do like that. Yeah, there we go. So we just had to close our brackets. I kind of messed it up a little bit. We had two opening ones. I forgot the second opening one. So there we go. Just kind of messed with the syntax a little. It's kind of finicky, especially in the browser, without an actual linter telling you what to do. But don't worry about it. So now that we have that sorted out, we're just going to actually normalize our data. So normalized table, or let's call it normalized data, I guess, is equal to normalized data. And then we pass in our original iris data, which is, of course, the name of this guy here. All right, so we're going to pass it in. So that means every single value here, petal length and sepal length, will be a value between 0 and 1. 1 being on the high end, 0 being on the low end. All right, so it's just saying short versus long. So don't worry about the actual. Just think about it like that. It's short versus long. All right, and then we got to prepare our training data. So our next thing, prepare training data. And then what I'm going to do for this is do const training data. It's going to be equal to our normalized data. And then what I'm going to do is another map. All right. So we're going to call it data this time. And then Everything's kind of in the way here, but we just have to define our inputs and our outputs. So we know our inputs are the 2 petal lengths, and we know our output is going to be a species. All right, so that we're more or less right now defining our nodes. All right, not the middle ones, but we're defining our input nodes and our output nodes. So our input nodes, we know there's going to be 2 of them, so that we can just do input colon, and then it's going to be a table that it takes in, and then we can just type in data dot sepal length, data dot petal length. Sorry. Because we can just call it data now because, of course, we're just mapping it like this. All right. So once we get that, what we're going to do is define our output. And we know our output can be one of 3 options, right? It can be one of those 3 types of flowers. So in order to get those 3 types of flowers, we can just say data.species is equal to setosa like this, okay? And that just means if our output, so if our species, which in our case we'll say setosa, if our species is equal to setosa, the value of this output node will be 1, all right? Otherwise, it will be equal to 0, all right? And it's the exact same thing for these guys. So we're going to get data.species, and then we're going to do versicolor, and then if that is the output, it'll be equal to 1, otherwise 0. And then lastly, data.species. And then question mark 1:0. Just like that. All right. And what this is telling us now, when we have a input that's getting trained, so we say we have this go in first, and it runs through our neural network, and it doesn't really matter if it gets the answer right or wrong at the start, but it's going to say the actual output should have been setosa, so it should have said the top output node should be a 1, the second output node should be a 0, and the third output node should be a 0. Likewise, if the flower was a versicolor, then this would be 1. These other 2 would be 0s. And that's how it's going to calculate the error that we talked about in the last video, all right? So it's going to find the difference between what the value is and what it should have been, all right? So either way, that is our 3 output nodes. And yeah, now we can just get rid of this. So that's our training data. And now that we have our training data, we can actually create our neural network, which is really easy to do. So we can do new brain.neural network. And then we can define what activation function we want. You can try a bunch of the ones that they have listed. I know there's tan-h you could try. You could try Relu, I don't know how to pronounce it. You could try sigmoid. Sigmoid's probably the most popular for something super straightforward. And then there's softmax. They all have their unique use cases, but I'm just going to try tan-h for now. If it doesn't work, we'll just switch it later. It's pretty easy to do, right? And then we can define how many hidden layers we want as well. So we defined the input and the output up here. We're going to define our hidden layers here. So make sure you type out hidden layers, colon, and then it's just going to be we'll say 5 hidden layers with 5 nodes in each. It's pretty big, so you probably won't even need that. But, you know, better safe than sorry, I guess. Right. Anyways, now that we have our network, now that we have that actually created, what we have to do is train the model. That's the next step, right? We're going to train our model based on our training data. And this is pretty easy too. We just do net.train, and we're going to do training data. So it already is set up for us, right? It already has our input, and then what the output is going to be. All right? So now that we have our training data, then we can define some other parameters in these open and closed brackets here, or braces. And what we're going to do is log :true. That means it's just going to keep track of our progress and our error to see if our model is actually training properly. And I'm going to do log period 100. So don't worry about this right now. And I'm going to say iterations. So how many epochs we want to do. How many times do you actually want to train on this data? We can say 1,000 at the start. And then a comma after that as well. And then our learning rate. So we didn't really cover this at all earlier, but this just means how quickly do we want to change our weights. So we're going to calculate an error, obviously, based on what the output is and what it should have been. And this more or less just means when we're changing our weights, to what degree do we want to change them. And usually you want to set a pretty arbitrary number. I'm just going to do 0.01 for right now because we're going to change it very little, all right, so it can fit properly. And we should be good to go. So you see I have a little error here on line 1 of 16. I just misspelled normalized to normalized. And then we can see our actual training here. So since we're doing, I don't know, it should be fine. I see we have a training error equal to nothing, so that's not good. And I'm not sure why yet, but I think it has to do with our data and normalized data. And yeah, I just made a small typo here as well, a little oversight. It should have been minus sepal length min here instead of d dot sepal length. And there we go. I'm not sure why it's doing it like this, but we should be good to go. And we can see now how our training data does after even 10 epochs versus even more than that, which is kind of cool. I'm not sure why this portion isn't working though, so I must have messed up that. I think it's called, oh, it's log period with a capital maybe. Okay, there we go. That's why it wasn't working. So now you can kind of mess with the values now and see what happens. So if we only do 100 epochs, we'll say, and we'll just log every 10, you can see that our error rate after the first 10 epochs was 14%, but then after we get down to our 100th iteration, you can see that our error is already 6%. So that means it's actually training itself really efficiently, and then we can try other activations as well and see what happens. So like you can see with sigmoid here, you can see after 10 iterations or 100 iterations, it's still 14%. So maybe for sigmoid, you'd have to jump it up. As you can see, it just stays the same. So maybe 10H is our go-to for training. And as you can see, if we get down to 0.008 here, so 0.8%, we're probably overfitting our neural network now. So you just gotta be careful of that, and maybe stick to 100 for now, because it's, you know, fitting so properly and nicely. All right. So with this actually happening, and we can see that our model is training properly, I think that's going to do it for this video. I think I'm going to split it up into 2 really quickly. And yeah, I'd like to thank you guys for watching. And in the next video, we will focus on the actual testing. And then we'll see if our neural network actually works properly if we put in test values and see if it actually outputs something that is accurate for us. So yeah, anyways, thank you.